Salam semua, saya akan presentation figure 1. First, 3 individual harmonies and figure 2 Fourier series approximation with n sama dengan 5, 10 dan 20 harmoni. Saya daripada kumpulan 6 session 2. My name is Teh Jin Kuan. My meeting number is CE240040.
Coding ini merupakan sebahagian daripada projek analisis sinar menggunakan Fourier series dan RC filter. Fokus utama adalah untuk menganalisis bentuk sinar nanti apabila diberikan tarik cycle sebanyak 25% dengan menggunakan magnet. Sinar ini dikembangkan kepada beberapa komponen harmoni untuk melihat kesannya terhadap bentuk gelombang akhir. Pertama, ada beberapa parameter penting ditetapkan. Yang pertama adalah frekuensi asas 500 kHz, cut-off frequency for filter 1000 kHz dan maksimum harmoni adalah 30 dan biaran kiraan untuk paparan masa adalah low second type magnet dan duty cycle utama adalah 25% iaitu 0.25. Yang lain-lain ni semua ni adalah yang formula T0 sama dengan 1/F0, omega 0 sama dengan low pi F0. Selepas itu, sinar nanti ini dibina semula menggunakan petikan Fourier series. So, setiap harmoni dikira menggunakan fungsi SINC. C ini yang mengambil kira titik cycle dan nombor harmoni. Sinar kemudian disintesiskan untuk berbagai nilai maksimum N seperti N sama dengan 1, 2, 3, 5, 10, 20 dan 30. Komponen-komponen ini dicurangkan satu persatu untuk melihat bagaimana bentuk gelombang semakin mendekati bentuk asas apabila lebih banyak harmoni digunakan. Seperti sintesis, RC filter diaplikasikan untuk menapis sinar berdasarkan frekuensi. So, frekuensi permintaan Hn digunakan untuk setiap komponen harmoni dengan formula adalah 1/1 tambah C omega per omega C. Kalau hasil filter ini menghasilkan sinar baru yang menggantungkan komponen frekuensi yang rendah dan menapis keluar frekuensi yang tinggi. Ini menggambarkan bagaimana filter berfungsi dalam sistem sebenar, terutamanya dalam pembuatan sinar analog dan digital. Kita run coding yang ini semua kan keluarkan low output adalah figure 1 dan 2. For figure 1 ni menunjukkan bentuk gelombang yang sintesis dengan N sama dengan 1, 2 dan 3 dan jumlah karbonnya. Yang figure yang kedua ni menunjukkan bentuk gelombang N sama dengan 5, 10, 20 dan akhir sekali adalah eksperimen modulus Sn dilukis sebagai unit impulse menunjukkan magnitude setiap komponen frekuensi dalam unit kilohertz. So, akhir sekali ini coding ini yang figure 1 dan 2 coding ini menunjukkan bagaimana kita boleh membina semula sinar nanti menggunakan Fourier serta melihat kesan RC filter dalam frekuensi domain. Analisis ini penting untuk memahami asas pembuatan sinar dalam jaluran elektrik dan elektronik.
Hi, my name is Mesa Ananiksen and my ID matrix is CE240148. So let's move on to the low pass filter, the crucial element in shaping our square wave signal. So we designed a first order RC low pass filter with a cutoff frequency FC set at 650 kHz. So the goal is to allow low frequency components to pass through while attenuating high frequency harmonics that give the square wave its sharp edge. look at the gain response, we can see it stay at 0 dB for low frequency, which means the signal passes unchanged. But as the frequency increases and it hits 650 kHz, the gain begins to drop, hitting -3 dB right at our cutoff point. So on the phase response, we observe a shift that becomes more significant as frequency increases, reaching -45 at the cutoff. So next, we analyze the output signal in the frequency domain after it passed through the filter. Comparing it to the original input spectrum, we notice a clear trend: harmonics below the cutoff frequency, like those at 100, 300, and 500 kHz, remain nearly untouched. But the harmonics above the cutoff, such as 700 and 900 kHz, were significantly attenuate, which is exactly what we expect from a low-pass filter. This tells us that the filter successfully removed high-frequency content, making the signal smoother and in shape. So in the time domain, we compare the input signal xt with the filter output yt. The result: the output signal looked rounder. The sharp edges of the square wave were noticeably softened. So this happens because the sharp corners are formed by high frequency harmonics, and since the filter removed those, the result is a smoother waveform. So the fundamental shape remains, but the waveform transitions are now gradual rather than abrupt. To summarize, our low-pass filter successfully remove unwanted high-frequency harmonics. In the frequency domain, we confirm that only harmonics above 650 kHz were attenuated. In the time domain, this translates into a cleaner, smoother waveform, a clear demonstration of how time frequency domains are deeply connected. This proves the power of Fourier analysis and practical filtering techniques in real signal processing applications. That's all from me. Thank you.
For the RC low pass filter circuit, we need to assume that R equal to 1000 ohms, and then we can get the value of capacitance from the frequency cutoff, which is the frequency cutoff is equal to 1000 kHz. From that, we use 1/2 pi RC to get the value of capacitance, and then we get the value of capacitance is 1.5915 exponent -10. After that, we click the OK and run the simulation. After that, we click the scope, and then we need to zoom in the graph to get more clearly look. And then after that, we need to compare this graph to a waveform output of waveform Fourier series equation. Then as you can see, the graph is almost like same, and as you can see, the left graph is a waveform for Fourier series, and the right graph is for RC low pass filter circuit graph. And as you can see, this graph is almost like same. For the next part is simulating analysis for variety frequency cutoff. We use 600 kHz frequency cutoff, and we need to determine the denominator coefficient 2.652 exponent -7, and after that we run the simulation, and then we click the scope to see the value of it. After that, we need to zoom in to get the more clearly graph output. As you can see here, the lower cut-off frequency allows fewer high frequency component to pass. The blue output becomes smoother, and more sinusoidal. The filter strongly attenuates sharp change, rounding off edge of the square wave, and the signal lacks more delayed response. After that, we use 1500 kHz frequency cutoff. Then we change the denominator to the new, which is 1.061 exponent negative 7, and we click the OK, and then we run the simulation. After that, we click the scope to see the graph, and we need to zoom in to get the more output for.
Hello, my name is Nur Hakim Arif bin Muhammad Razali. My matrix number is CE240049. So I want to analyzing how the duty cycle affect a signal in both the time and frequency domain. So in the left plot is a time domain. As duty cycle increase, the pulse width becomes wider. 10% duty short until to narrow pulse. 50% duty to square wave. So it's a equal on and off time. This confirms that the pulse width is directly proportional to the duty cycle. So now we see the right plot is a frequency domain. So here's where it get interesting. So the DC component at 0 Hz is equal to the duty cycle value. Smaller duty cycle spread energy across higher frequency, so can be a wide spectrum. Larger duty cycle focus energy a lower frequency. It will be become a narrow spectrum. In summary, changing the duty cycle change the signal shape and its spectral content. It's a simple adjustment, but it affects a lot. Thank you.